Would be awesome. So, welcome everyone. Like I said, we're really glad to be here with you guys today on a Monday. We have a lot to cover today, so get right into it. Feel free to interrupt at any point. Um, we love uh, any kind of help, any kind of questions. We love to help. So if you're questioning what this is, I am still questioning it. I've seen it about 20 times. Uh, it was David's portrayal of what our meeting is going to be today. So I hope you guys enjoy it. And before we get into uh, any further into actually the workshop, I think it's important enough to show you what Kaggle is, because this will really be one of the greatest tools that you will use if you're going to be a machine learning engineer or any type of interest that you have in machine learning. This is your friend. And I'll show you how we came across our data today. So you'll go on Kaggle. I don't know if you need an account to browse. I don't think so. But anyways, if you make an account, it's free. It's really great to have. And so you have a lot of data sets to choose from. And what's great about Kaggle is you have all these data sets in one place. Plus, they tell you, for example, here in the restaurant business rankings, they tell you usability, which tends so you have different. If it's 10, most likely you'll have very little pre-processing. So yeah, just wanted to show you, and let's show. Ours is I have, we have it linked, but let me see. Medicine costs. This one. You know what? I will just click on the link, which you guys can do too. Um, but yeah, it was medical cost personal data set. And so you find this data set. Uh, you'll often have a kind of content and context of it, and then you'll have a description of what the data holds, and you can download it. You can download the thing and also look at what other people have to say about it. So very useful. But now onto our workshop. So let me see if I could. Can you guys all see very well? Everything fine? Yeah. Okay, great. So welcome to the AI model workshop. This is our fifth dev community. I lost track already, but we've loved having you guys, and let's jump right into it. So the first thing that we're going to do is we're going to import our pandas, our matplotlib, and our numpy. Now these are extremely important. Uh, Overall, we've talked about them in a few weeks, and just know we have this there. We import the data set into our first data frame. Okay, we know how to do that. Now, here's something that you might not know. We didn't cover this, but you don't really need to know too much about it. But I will explain it briefly. So what I did is in our original data set, and I will show it real quick. Um, you have what's called categorical data, which David covered last time. And as you may remember, like male, female, and uh, smoker, yes, no, and other type of data in our data set, it's words and strings, and we don't, or objects, and we don't really want that. We want, numbers that we can work with. So get dummies is just a pandas function that we use so that we can convert the smoker, region, and sex from our data frame, and then create our new one that we're actually going to use. As you can see, so now we have it really nicely split up and that we can use. So just wanted to show you. Let's get our shape. This will show you how big our data set is, and how many columns, how many rows, and that's more for our purpose. So you don't have to think about that too much. But now here's part of the pre-processing. What we did here is we get from sklearn, we get a function called train test split, and I'll show you what that does in a little bit. But we need our y and our x for our data that we're going to use all throughout in the models. Again, the shape, so we can kind of see. Keep in mind that they are super different. That was a headache. You can ask David when we were doing it. That's a lot of the pre-processing, and don't worry, you guys won't have to do it today. So let's just keep moving on so that you can see for your convenience.
You skipped the train test split.
Okay. Yeah. Oh, my bad. Thank you. I was wondering. I was like, wait, where's our train test split? But this part's important. You use a function. You specify the data as we did. What test size is it'll take. In this case, we put 15% will go to the test size, and then the other percentage will go to training. And if you guys remember, random state, that's a seed, so you don't need to worry too much about that. But so we can get our x train, our x test, our y train, and our y test. This is very important for any model, as you'll see. I'll show you. And then now we can get to this part, which is just to see what they're made of. As you see, it's a smaller part of the data set because we split it. But it's even split between x test and y test, so on. So it's a really useful function. Now onto our first model. Now this is probably one of the most simple models, and I don't want to go to the GIF yet because I don't want to distract you guys. But this is one of our most simple machine learning models, and you'll probably be surprised that it's considered machine learning, but it is, and it is linear regression. So as you can see with this GIF, you have a series of you have a scatter plot full of all types of data points, and our blue line is our linear regression. You'll have over the iteration that we have right here. The more iterations, the more perfected it goes if you do everything well. And so I don't know if you guys recognize it, but this is just a line best fit. I mean, this is like in high school or in college, if you remember back, this is the y equal mx plus b. It's just basically what it is, but it's giving a relationship that is best fit to our data to use it to predict. So it's still machine learning. And so then let's just quickly, this was just for visual purposes. This is what our x test age looks like. It's just one column. So, and then we actually get to our model, which I showed you. So we have our GIF. What we're going to do today is we're going to try to see the relationship between the age and the charges, which in our data set, we have the charges and the age. So by charges, it means how much that person was charged for a medical procedure. So it's a very easy relationship, it's X and Y, but it's very important to understand that, we can do this. So let's see. So we're importing our linear model, and then we're importing specifically linear regression, and that's the model that we're going to be using. And so we have I named it regressor lin. You could just name it regressor if you're dealing with one model, but because we're dealing with several forms of regression, it's better to name it that. So just so you know. And this is what we imported. This is our linear regression model. And as you can see, not that daunting yet, right? Because we don't have to code it from scratch. That's why sklearn is so useful. If you had to code this from scratch, would be a bit more difficult. So we can just call it and fit our data onto it using .fit. And then our data that we use our training data. So you start to see why we split it. Then we have our Y prediction, which once you have your variable that holds the model along with the trained the data that it trained on, and I'll run it just quickly, right? The model that we trained on, you can pass the X test, which is again part of it that we split already, run it in the model and just use .predict and it will predict it already. But just to show how it did, I scattered already our X test, and this is part of it that we split, our age, and our Y test, which is our labels, which is the ones that hold the charges. And as you can see, it's just green. We have it all scattered. These are all the points in our data set. And so, it's very clean. So what we're going to do next is we're going to see how our linear regression model handle these, what it thinks all the points should be. So let's see. Okay, so we already actually predicted it, but we haven't visualized it for you guys. But the model already gave its prediction right here. But what we're doing is we put it into a data frame because it's easier to handle. We can then show it on the scatter plot. So it's really easy. You just make a new data frame. You have the actual, which is our Y test that we split off earlier. And then we have what the model predicted, which if you remember, we put in our variable. And let's see, let's make sure that, so it's a working data frame. Any second now. Yeah, there you go. And so we have our actual and we have our predicted, and you can see already visually how different it is and how much off it is. It's not that bad actually for what it is, but it's still pretty off. But let's see it in a more visual way. So, did somebody have a question? No? Okay, feel free if you remember your question or if you have another question to interrupt. Yeah, so, and now we're gonna plot it. Let's see on a more grand scale what it's doing rather than looking one by one into our data frame. Let's see, I'm doing, this is the same exact line that we did before, so we can get the scatter points, the original data. And then let's use the scatter points of our predicted. As you see, we have our same point, same X, but our Y is going to be our predicted result. And probably should have mentioned that before if you're not familiar. So X is normally your independent variable and Y is dependent on your X. So in this case, our X is the age and the Y is our charges. So in this case, we're looking at how X changes the charges. Just so you know. So we have it mapped. In green, we have, again, our previous data. This is the actual data. And then in red, we have what the model predicts. And as you see, it's not that far off. Of course, we have a lot of anomalies out here where it's kind of like in the blank space. And that's one thing that with linear regression, if you can imagine a line running right here, this is probably how the line looks like. So it hit a lot of these points, but it missed out on this data since it's a bit less clustered, right? But not bad already. I mean, for being linear regression, it's not bad. We can see that predicted a lot of these densely populated areas. So any questions about that before I move on? I hope I'm not. No, nothing. Any comments?
So is the reason why linear regression ended up getting the results, in the space between the 2000 and 4000 mark because it sort of found like an average value for those?
Yeah, it's very similar to that actually, and I didn't put it in here, but you can get the I think the average mean error. David, it's average mean error, yes.
The mean absolute error.
Mean absolute bad. Mean absolute error, and that's completely correct. So you have like, if you can imagine the line right here, um, you can see that they're kind of similar data, similar distance from the this imaginary line, which is actually probably there, but it's not visualized. And that's why, rather than being so sparse, um, it focused, okay, this is definitely an area that we need to focus on, and then it just kind of replicated on here, but more sparse. So great. Um, so yeah, let's keep moving. So this is going to be random forest regression, and it starts to get a bit more complicated. But again, this isn't too bad either. But for this case, we have decision trees, and I show one of the decision trees. So you can have, for example, so decision trees, you'd have several branches that have different choices to make and or different conditions, right? So you'd have like salary is between 50 to 80,000, right? And then there'll be true or false or yes and no. So if the salary is between this amount, then we can move on to our next decision. But if not, in this case, we're saying, okay, no, we don't want that. Then so we have like office near home. This might be a condition that we're looking for. And if it's no, again, decline offer or accept offer. I mean, move on to our next one. And then this is really the root of what we're looking for is, okay, here we have our, you have these decline offers, but then you also have the accept offer. And so with decision trees, you're often making almost like asking questions. You have a salary between blah, blah, yes or no, and then you have different choices to make, right? I hope I explained that right. I mean, well enough. But for random forest regression, so remember this is called a decision tree, and I guess how to remember it is, several trees make a forest. So that's one way that I often look at it. So random forest regression. So what we're looking at is we have several of these decision trees working at the same time. So they're working in parallel to predict a certain outcome. Yeah, I hope that makes sense. But you'll see the results are similar to linear regression. So at least on this one, it performs better with big data. But so what we have is again from sklearn. This time we're getting from ensemble, and actually this is something that maybe I should mention. Random forest regressors are considered an ensemble class. Like there's several types of models that are ensembles and or ensemble. Sorry, I messed up. But and so what this means is they can work with several other models together to have one predicted outcome. So it's not too important to if you're confused on right now, but just know that's why sklearn puts it in ensemble. And then we have a random forest regressor. So we're just importing it so that we can use it. And let's start off with 10 trees to begin with. So as you see, regressor again, but this time we specify forest. We call our model, but this time we don't have to dot fit it yet because we want to see it like easier. So we first call our model, and the parameters that we're saying is here. This is we're asking for 10 trees, so 10 of these, and then this is the seed. So then we're fitting it to our training data, like we did before. Same thing. And then we can actually make our prediction, which we hold in this variable. We have our prediction based on X tests, just like we did with linear regression.
Sorry to interrupt again, but so having 10 trees, are the trees running the same tests every single time, each tree?
No. They're based on wait, my understanding.
Randomness. They're randomly running different parameters. And xgboost also use random forest, and it just randomly jiggles things around and tries to come up with the best answer.
That's why it's called random forest.
Yeah.
Okay.
Yeah. Oh, yeah. I couldn't have explained it better. Thank you, Mark and David. So yeah, I hope that answers it. Does it answer?
Yeah, it does.
Okay. Good. Yeah. So we're training our regressor forest to our training data, fitting it a lot. And then we are predicting based on our test. And we're going to hold this variable so that we can show you how it came out. We'll see. So again, using the same scatter plot, we're putting our X as our age and then our Y test. So same as before, but now we're looking at a scatter plot where you have the age and then you have our prediction. And so that we can compare it and see how our model did. And we'll, hopefully this goes. The good thing about these models is they don't take very long to do. Okay, so we have our predictions, and I put it in black this time. Kind of stands out. And this is already a lot better prediction, at least as you can see, as our linear regression. And we have, and this is with 10 trees, keep in mind. So we have our densely populated data like in these clusters, and it seems to be doing quite good, but it also has, it's able to reach these areas that aren't as clustered as here. So this is already a good sign. And for 10 trees, it's really good. So yeah. And now we're gonna do the same thing, but now with 100 trees. And it's really the same code, which is awesome for us. You do just change the n estimators. Now we have 100 trees. We train it on our data, and we have our predict, which just like before. And we're gonna run it so that we have it in our variable. And then we're gonna do the same thing. Again, in green, we keep it consistent. And then we have our prediction in black, and we can see how it goes. As soon as it loads, we'll see. As soon as it loads, there you go. So at first glance, might not look like a lot changed, and it really hasn't. I mean, it's kind of difficult to show both of them, but there are some differences, very slight, I think. Let me find, unless this didn't run, which is very possible. But it is very similar, so let me see. Kind of slow. Hello?
I think you didn't run the first.
Yeah, but I don't know. It's not giving me any feedback. That might be my computer. So could you try running it, David? Maybe you're, while we wait for that to work. Let me know if it ran.
Yeah, it ran. It's there now.
Okay, awesome. And I'll clear out this output and run it again. Okay, yeah. Now it should be changed. Let me see.
No, brother, you need to run the second one again. The one with 100.
Yeah, I thought that's what you were saying that you ran. This one?
I ran the first one, so the first graph has changed.
Mm-hmm. Yeah.
Now
So,
you gotta run the second one again and then graph it again.
it's being slow. It should be a bit different. So let me.
They're different.
There you go. Okay. Okay. Yeah. There you go. There you go. Just some deep note issues. But no worries. So there are differences here, and you'll see. Let's see right here. That should be different. Yeah. So as you can see, just looking at this, you have this little cluster, and here it already changed. And overall, there are a lot of changes. Like here, it's gone a bit more closely together than here, where you had this large amount of sparse data. But in reality, in our training and in our for our purposes, it didn't really improve too much. I mean, yes, it did get a bit more accurate on these points, as you can see here, but really nothing too crazy for increasing it by 10 times as many trees. So what's possible, what may have happened here was actually that it overfit the data, but it did get a bit better. But you know, if we increase this by 1,000 trees, which I did, we can try again if we have time at the end. But it doesn't really improve it too much. You know, you would think that these points would match right on to the actual data, but it just overfit it. So yeah. So
Okay, thanks, Hermes.
yeah, I was gonna say, there you go. Good luck, David.
All right, let me share, please.
Yep.
Can you see my screen?
Yeah.
All right, perfect. So let me piggyback off where we left off with Hermes. So as we see here, after we put more random forests, and we have this new graph. So like Hermes said, it is overfit, but it didn't really improve. I mean, it did improve. Yeah, it can predict the training data and the validation data better. However, that misses the entire point of making an AI model in the first place. You want your models to generalize, meaning you want it to predict well data that's never seen before. And by basically training it and basically training it with the same data and validating it with the same data, you're creating a data leakage. And a data leakage is when you're kind of guiding the model into predicting the validation data well. And what ends up happening is, yeah, the model can predict the validation data well, but if new data comes along, it's going to be terrible. It's not going to get it.
We also have our test data. We haven't tried validating our test data yet to see if we are overfitting. Because if we are overfitting our test run, we'll have a very bad result.
Yeah. Well, I'm about to show gradient boosting regression. So what is gradient boosting? It's another different type of regression tactic. So basically what happens is it gets a bunch of weaker models or weaker predictors and merges it into a very strong one. That's just a very general gist. So let me import the xgboost package and we'll create our model right here. So XGB model, we're going to be using the XGB regressor class, and estimators, we're going to do 50. So it's going to get 50 of these weaker models and put them together. Oh, wait, no. It's going to do it 50 times, but it's going to get 12 weaker models and put them together. And we're going to use a learning rate of 0.1. The learning rate is basically, well, how much do we want the model to learn every time it averages out these weaker models. And you usually want to put this at a lower value the more you do this. So at n estimators here, I put it at 0.8 because it's like, I'd say, I don't know. What's 800 divided by 50? I don't know. I can't think of it at the top of my head, but it's significantly larger. I might actually be better to put it at 0.6. So, and verbosity equals 0. This just means do it quietly. And a booster, this is something specific to xgboost. It's it basically gives the model a better structure of what's gonna be happening. And we put GB linear, which is like linear regression. And over here, we have the fit function. We're gonna use our train data for X and our train data for Y. And for the evaluation set, we're gonna use our X test and our Y test. And the evaluation metric we're gonna use is mean absolute error, which is basically saying, oh, this is the average number that it's off by the prediction. And early stopping rounds means, oh, if the model isn't improving after 10 rounds, stop it. All right, so let's fit. All right, so it looks like early stopping wasn't triggered. So it should be pretty good right now. Let's predict on the X test data. And let's see what the difference is. Okay, so like the other one looks pretty good, it looks pretty average. It's kind of in the middle of all the dots. That's good. But let's show what it is to overfit. So let's comment out this one, uncomment this one. I'll put it 0.8 to show it better. Let's do the same thing.
Wait, David, you forgot to uncomment like the actual call to the model. The line above.
Oh, whoops.
Yeah.
I skipped a line. All right, let's see. Okay, it looks like it stopped at 4,077 as the mean absolute error. Let's predict our X test data again. And let's plot it out and see. Okay, and here is where you can clearly see overfitting. So the red dots are our model's predictions and the blue dots are the actual values. And you can see that the red dots are literally almost right on top of the blue dots, literally everywhere. And that's overfitting. And if I was to use this model over the other one, which was more general on new data, it will be really, really bad. Does anyone have any questions? Okay.
I just posted a link. You can tune XGBoost by using the T-train set weight. I put a link in there.
All right, that's
found that
awesome.
You can really overfit with that, but you can also get a better fit that will work with test data.
All right, let me show what underfitting looks like now. So let's say our 0.001. This is a really, really low learning rate. It means that every time it's going to go through only a little bit of improvement every single time. So let's see here. I'm pretty sure it's going to go through all the iterations. Yeah, it went through all of them. Let's predict our X test. Plot it out. And there we go. You can see that it's not really general and kind of missing out on all these and all these. So it's kind of underfit. And some would argue that this is actually better than both of the ones I had before, because these are almost outliers. But I would say it's better to have it more around here, because outliers happen. And a model that can catch those outliers is a pretty good model to me. And now we're going to go into neural network. I'm sure most of you have heard of this before. The one we're going to be doing in particular is a feed-forward neural network, meaning it only goes one way. It goes to input layer, hidden layer, and output layer. The input layer is where our data is going to come in, the 11 columns that we have for our X train. Then we have our hidden layer. You can think of your hidden layers as like a measure of importance for these input layers. And the output layer, we only have one node in our output layer, which is going to be the number of, which is going to be the charges of the medical cost. Anyone has anything to say?
All right. So generally, with the neural network, you have back tracing to set the weights, and that's the whole point of fitting it, is to set the weights to different parameters.
Yes.
So just
Thank
going
you, Mark.
forward doesn't work very well.
Yes. Usually in a more developed neural network, you would have back propagation and probably a really good optimizer as well. But for a linear regression problem like this, that's not overcomplicated. So let's import our packages. We're going to be using TensorFlow and Keras. Hey, if you need a book on Keras or want to know more, I got you. DM me on Discord. So let's create our model. We're going to create our sequential model. Sequential, which just means one by one. And we're going to have 3 layers. We're going to have the first layer right here, which is going to be our input layer. It's going to be a dense layer. 32 is the number of little nodes here. And we're going to have an activation of reloop. I don't want to get into the activation functions right now. But a general gist of what it is how to initialize the weights in these nodes. And for our input shape, we're going to put 11. 11 is the number of columns we have in the X train. I can show it right here. oops, I put trend. Hermes. We have, see, 11 columns, 1,137 rows. And for our test, it should be the same number of columns. $11 columns. And I'm gonna give this layer a name of input. Our second layer is gonna be our hidden layer. We're gonna have 32 nodes, an activation or reload, and we're gonna name it hidden. And for our output layer, we're gonna have a dense layer with one node, which is gonna be just a constant value. Here. And Keras has this cool function called summary. Basically shows you a brief overview of the model in question. So here we have the input. You have our hit, and we have our output. So if you wanted to visualize it even more, you could go back to the picture and you could imagine 32 of these dots here, 32 here, and then 1 here. It's a very, very basic neural network. So let's compile the model. We're going to be using RMS prop as our optimizer. We can also use Atom, but we're just going to use RMS prop. Keep it simple. And we're going to have a loss function of MSE, mean standard error. And we're going to have a metric of mean absolute error. And then we're going to fit the model. We're going to have the hit. We're going to save it in a variable. And we're going to fit it. X equals X train, Y equals Y train. Batch size is how many rows we're going to take into the neural network every epoch. And epoch is basically how many times we want to run the data through the neural network. So 50 times, go 32 by 32 rows. For both, we're gonna keep it silent, but just to be cool, we're gonna put it at 1. And validation data, we're gonna have our X test and our Y test. All right. Very cool, very cool. You can see, did it 50 times. Let's show our keys. This is important for now that we're gonna plot it. We're gonna see what's going on. All right. We're gonna use matplotlib right here. So as we can see, as the epochs went, the mean average error went down and then up. This is a sign of overfitting, but it could also be a very local. And maybe if we did more epochs, it would go down even more. And that's what we're going to do right now. So for rows 1s, so we're cool. And now we're going to do 250 epochs. And you can also put early stopping rounds as a callback function using Keras. However, I didn't want to overcomplicate it. So let's plot this right here. And as you can see, we were right about the local just increase in the mean average error, but this can also be a sign of overfitting. As we mentioned before, if the mean absolute error of the neural network, which is like the measure of how off the predictions are from the actual values, is too close, it might be a sign of overfitting. And overfitting is basically the main problem in AI right now. So there's a couple of ways we can stop overfitting. One way is to use less epochs. But there's also another way. It's called dropout layers. The methodology behind dropout layers is if you drop out some of the weights inside of your model while it's passing through, it removes like correlations that could lead to overfitting. Another way is to modify the learning rate and also to use other hyperparameters and callback functions like I mentioned before, where early stopping rounds or to get the best model state without overfitting. All right. Any questions?
Oh, I have one, David.
Yeah, sure.
So I always heard that with AI and machine learning, it takes hours and hours, but all of the models that we covered today were super quick.
Oh, yeah. Well, actually, it's two things. There's two reasons why it was so quick. The first reason is our data set, which is insurance, DF. It's actually really small. Only 1,338 rows. That's really small. And also, linear regression and regression models are usually the fastest to train because it has the least amount of things to worry about. But once we go into computer vision and natural language processing, you probably won't catch us training those models in the moment because those take probably how much time did it take for the eBay data set to train?
I don't know. It took. I think we even had to stop it at one point. No,
I think we had to save it at one point because it was like taking 40 minutes.
Yeah,
that was a huge data set. That was like 1 million rows.
Yeah, but
we're gonna keep it small for you guys.
Yeah, and it can get a lot worse now. Like, I mean, we didn't use a G. Did we use a GPU? No, we didn't use a GPU.
We tried to. All right. That's it, guys, for this dev community meeting. Are there any questions?
Yeah. Speaker, thank you for teaching me how to do like linear regression and being a modeling. And how do you send code and as well as the applications? I have no question whatsoever. So
I didn't quite hear that. Can you write it out in the chat real quick?
Thank you for actually explaining the important into the application, okay?
Okay. I think he was thanking us for if I heard it right.
Yeah.
I understand now. Yeah, no problem, man. Like, it's part of the gig, eh?
Yeah, exactly.
If you have any questions, hey, feel free to DM us on Discord.
Yeah, we'd be glad to help. And any other questions? Any other comments? Anything?
So training these machines, it only takes time when you're processing like large data sets. And why does it take a while with computer vision?
So think about it like this. In a picture, it has a resolution. And that resolution basically means it's going to be this many pixels. And this many pixels is a giant array of RGB values. And besides the array of RGB values, you can have different colors. So you have the intensity and the color. That's multi-dimensional arrays there that you need to take into account, and also the process of which Well, it actually also depends on what you're trying to get out of a picture. But let's say you're trying to identify what's inside of the picture, or like what it is, or classifying what it is. The model itself is gonna use layers like conv2D to reduce the dimensionality and see what features it can get out of the picture to identify it. It's gonna pool it, increase the dimensionality to put more importance on features, conv2D, pooling, and then it's gonna end up in a dense, dense with a categorical to see which type of or category it would be. And if you want a good model to classify pictures, you're gonna need a lot of pictures, because just one picture, the model's not gonna be able to get sufficient features from just one picture. So you need a lot of pictures. It's a complicated model, and depending on what you're trying to get out of it, it's also gonna take time to train it to be right and prevent
Gotcha.
overfitting.
Gotcha. Thank you.
Yeah.
We'll go over it next time. Don't worry about it. Hey,
Yeah.
let's actually
Sweet.
plug in our next workshop right now.
Yeah.
So for the next workshop, we're going to be going into computer vision. We're going to be creating a model to differentiate between cats and dogs. Hype.
Yeah. We'll see. Maybe we'll sprinkle some extra stuff in there. But I hope you guys are excited for that one, because I don't know. I love computer vision. I think it's one of the coolest applications of AI. So what about you, David?
Oh, yes, for sure. Right next to natural language processing, probably the best.
We did that
and-
in Randa School, cats and dogs on pictures.
Yeah.
Oh, yeah.
Yeah, it's used everywhere, but it's very important. It's pretty cool analysis
The
of
most basic, you already know. And you're going to see how we handle not having enough data. We're going to do a bunch of transformations on the pictures so we can have more data, because like I said before, you need to have a good classifying model for pictures. You need a lot of data to get those features, right? And one last thing, if you actually want to have practical experience using models and get a little bit more projects in with AI, please consider joining the Google Solution Challenge. It started a couple weeks ago, but hey, you can still do it if you try.
Yeah, I
If
second.
you got more questions about it, please visit the Solution Challenge channels in the Discord.
And you can ask any of us. We're always happy to help. It's a great opportunity. So I definitely agree with David on that one. And yeah, I think that will finish our workshop, right, David?
Yes, sir.
Perfect. Thank you all for coming out. And we hope you learned a little bit or a lot. We don't mind either. And reach out to us if you need any help.